For the second part of this unit, we're going to focus on some forms of energy and then move into some more specific environmental science parts tying in our chemistry and physics and biology. So energy is the ability to do work, and power is the rate at which work is done. So energy is power times time. So it's important that we know things like a kilowatt is a unit of power, but a kilowatt hour is a unit of energy, okay, because we add in that value of time. Going back to physics, kinetic energy is the energy of motion, and potential energy is energy that is stored. And this is different from chemical energy, where that potential is stored in the form of chemical bonds. And that's important because we have organisms that take in nutrients and get their energy from chemical energy, from the energy stored in those bonds. And then temperature is the measure of average kinetic energy of a substance. You know, if you had me in chemistry, that's one of the things that I made sure that you knew before you left my class. If we look at a dam, it's a great example of potential and kinetic energy. That water behind the dam has a ton of stored potential energy, and then the energy that's allowed to flow and turn the turbines, that's that kinetic energy that's being harvested. First law of thermodynamics, energy is neither created nor destroyed. Essentially, you can't get something from nothing, so we put in some potential or chemical energy in the form of gasoline, and then we output that energy into useful kinetic energy, which moves the car. But of course, anytime we have energy input, we have energy outputs, and we have some waste energy. So there's heat from friction in the engine, friction from the tires on the road, brakes for stopping. Then there's sound energy from the tires on the road surface. So we never get 100% of the energy we put in to become 100% of the energy that we put out. It's all there, but it's not 100% of it is produced, but not always 100% useful, never 100% useful. The second law of thermodynamics, when energy is transformed, the quantity of energy remains the same, but its ability to do work diminishes. So if we have a coal-fired power plant, the energy used to turn the turbines, about 35% of that energy can be harvested, and 65% of that energy is wasted as heat. So we, out of the initial, what we're starting with, we only get 35% of that energy. When we take that electrical energy and now transmit it to long distances, along power lines, we lose about 10% of that energy, but 90% of it makes its way. And then when we use that electricity to have our light bulb, certainly with these older bulbs, 95% of that energy was lost to heat, and only 5% of it went to light. So if you look at the efficiency of a light bulb compared to where it started with the energy produced from coal, it's only 1.6% efficiency. That's incredibly small. Second law of thermodynamics, the ratio of the amount of work that is done to the total amount of energy that is introduced into the system. That's that idea of what energy efficiency is. What is that ratio? The more efficient, the better that ratio will be. If we look at the efficiency of burning wood, a traditional fireplace, in order to get the same amount of heat, you'd have to burn this much wood, compared to if you have a modern wood stove, it only needs this much wood. It has to do because most of this heat is lost going up the chimney, whereas in here, that heat is contained and allowed to radiate, and much more efficient than a traditional fireplace. My husband has this debate with me all the time about wanting to put a wood stove insert into our fireplace so that would be more efficient. But I like the ambiance of the traditional fireplace since we're not truly using it for heat, although I guess we could if we had a wood stove. The second law of thermodynamics, looking again at the energy quality, the ease with which an energy source can be used for work. Entropy is another chemistry term. All systems move towards randomness rather than towards each other. So randomness is always increasing. We use that analogy of that your bedroom will spontaneously get messy and you have to take the energy to put into it to keep things organized. And this is just looking at some different environments. And if we look at these environments based on what kind of forms of energy can be harvested there, determines what sort of organisms can live there, whether they're how much light energy is, chemical energy, those sorts of things. System analysis showed that no matter how matter and energy flow in this environment, we're looking at open versus closed systems. So here in environmental science, we have two kinds of systems that we need to look at: open systems and closed systems. Most systems are open systems. Most things that we look at, almost everything is an open system. Exchanges of matters of energy occur across system boundaries. Solar energy comes into the earth, it's used for various ways, and then outputs heat energy, reflected light, those sorts of things. Matter, we don't have major inputs. I mean, you can think of, a handful of small meteorites falling as an input, but we also have no major output. So matter is very much a closed system. And then what we have is referred to as a steady state. Steady state in a system is when the input equals the output. So if we have a hose and it's filling a bucket, but then we have enough holes in the bottom where the output is the same as the input, this water level will always remain constant. It's not until we make some sort of change where we either turn on the faucet higher or plug the holes or add more holes that we are no longer in a steady state. In environmental science, we like to look at steady states because that's what's going to adjust various things. In steady states, we have both negative and positive feedback loops. And the thing that has to be taken into consideration is that negative does not mean bad and positive does not mean good. These are two of the big misconceptions when dealing with feedback loops. So a negative feedback loop can be a good thing, but it's when a system responds to a change by returning to its original state, or at least by decreasing the rate at which the change is occurring. This is different from a positive feedback loop, when a system responds to a change by increasing the rate at which the change is occurring. The positive amplifies the change, while the negative resists the change. It does not have anything to do with them being good or bad, and it's easier to see through an example. If you look at a lake level, such as the one we looked at with Mono Lake, the lake has a specific level. That level drops, it gets lower. Because of this reduced surface area, there's not as much surface, there's less evaporation. Because it's evaporating less, the level rises. Now the lake level is constant again. So it naturally balances, keeps that lake level at a constant rate. And it's referred to as a negative feedback loop because things are dropping, it's reducing this, there's less evaporation, which causes the level to rise. A positive feedback loop continues to feed into itself. So as population increases, there's more people to have more births. The more births, the population increases more, which leads to more birth, which leads to more population increase. So that's a positive feedback loop where things are continually increasing. And that will be the end of chapter 2. For this unit, and that will be all of our Unit 1 material, which is a lot of review and sort of a big overview of what we're going to be doing this year, and some terms for environmental science.